All right, good evening, everyone. My name is Cori, and I'm going to be going through practice exam 4 and just trying to explain some of the logic of the questions. And if you have any comments, questions, concerns, please feel free to reach out to any of the TAs. All right, with the first question, what it's asking for is which one of these is considered a buffer? And this one's pretty straightforward. A buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid. So it's easy to just go through and figure out which ones align as base and acid or base and conjugate acid. And none of these do until we get to answer E. So pretty straightforward on what is a buffer and why E makes sense. All right, so for number 2, what this is asking really is just like titration stoichiometry to find the molarity of an unknown acid. All right, so we're going to set this up. What I like to do is write my given information and then figure out what I need to either convert or what needs to change. So I'm given some critical details here, and then I just highlight those. So that would make it a little bit easier to do some math. So um, I know my acid volume is equal to 12.5 milliliters, which I will probably just convert right away to make it easier to me to liters. I know that my base, all right, and then I'm given my base volume. Again, probably easier to just convert it right away to milliliters. I mean to liters. All right, so this is basic like dimensional analysis. So we want to start with information that we're given to make it easier to get to that molarity, which is moles over liters. So I'm going to start with converting my base into moles. So first step I would do, cancel out my liters. I'm left with my moles. Uh-oh. So doing the math there, that should equal. All right, so now I have my moles of BaOH2, and then I need to convert that, right? So using my stoichiometry, um, this is a bit important, but this gives you two OHs, um, not one. So just make sure that you're paying attention to your stoichiometry here. So these cancel out. And this allows me to get the answer into moles of OH. So if I do that math, that gives me roughly 0.01186 moles of OH. And this was our monoprotic acid. So I was given the liters of it, but I wasn't, so my unknown. So in order to put that into my molarity, I want to make sure that I now divide it by the liters that I was given here earlier. I'm sorry, there's not a lot of room for math here, so it's a little sloppy, but that ends up giving me 895 molarity, which the answer is D. So if this was hard to visualize that the stoichiometry from this compound would end up being 2 to 1, right? Then you might want to write out the balanced equation of like when it what it produces. But for me, it was just a matter of going, oh, I have two OHs per that OH that would be produced, so it's a 2 to 1 stoichiometry. This step here is very critical to make sure that you get the proper moles of your unknown in order to put it into its molarity. All right, so question 3. Okay, so this is asking basically why a weak acid strong base titration has the equivalence point above 7. So we just need to read through each one's. Um, so at equivalence, all weak acids have been converted into its conjugate base. So I think this is acetic acid. Hopefully you guys can correct me if I'm wrong, but I think that's acetic acid. So uh, it's a weak acid, so this is a weak acid. And we know that it would have a conjugate base of CH3COO minus, right? Because let's change the color here. This hydrogen leaves, and then it creates a negative charge. So this is its conjugate base. All right, so then let's go through this. Um, and if I were to write out, the equation, it would look something like CH3COOH. Oh, a titrant. Okay. And this OH is the same as this KOH, right? K is the spectator ion, and it creates the negative. Wish there was more space on that. Not doing very good with the space given. Sorry, guys. See if I can write this better. It's in equilibrium with its conjugate base plus water. All right, so with this information, so this question is asking why the pH at equivalence is greater than 7. Um, in a weak acid, strong base, right? At equivalence, the acetic acid has been turned into its acetate, right? And acetate is the conjugate base of a weak acid, so it reacts with the water to make that um, hydroxide. And so that's why the solution is basic and the pH is above 7, because this is what we're seeing. So looking through here, this looks correct. A looks about right. B, I think it's more moles of strong base and weak acid. No. K, ion reacts with water. No, it's a spectator ion. H2O doesn't have a pH greater than 7. And we already said that this was not true, so the answer has to be A. Okay, so hopefully the space will be better for 4. All right, one of the buffer systems in the human body involves dihydrogen phosphate and monohydrogen phosphate ions. What happens when a strong base is added to the buffer system? Okay. In this phosphate buffer, the dihydrogen phosphate is the acid part of the buffer, so it reacts. So it reacts with the added hydroxide. That forms more hydrogen phosphate and water. So the pH would go up a little bit, but not a lot, because the buffer, resists that large pH change. So this would look something like H2PO4 is the acid, right? Plus that water. So, so that added OH is reacting with this. And we can see that the added strong base gets consumed by the acid part of the buffer. Um, oh wait, yeah. Yeah, the acid part of the buffer. So the pH changes just a little bit, but not dramatically. So looking through each of these, produce more water. No, that's not. Base reactivation produces, and the pH increases a small amount. Well, it does increase a little bit, but the base reacts with is wrong. The HPO4, it's backwards. So this is true. So the pH, increasing a little bit might throw you off here because you're like, yeah, it should increase a little bit. Well, you have to see what the base is reacting with, and it's not reacting with H2. It's not reacting with HPO4 2, it's reacting with H2PO4 minus. So I'm leaning towards C. The pH, it's not increasing dramatically. Nope. And the buffer decreases dramatically. Nope. So those are throwaways. So the answer to this one's C. All right. Let's go with 5. Okay. What is the maximum number of moles of strong acid could be added to the buffer before it shows a dramatic change in pH? All right, so this is like buffer capacity. I think this was talked about maybe a week or two ago. I don't quite remember. So if a strong acid is added, it reacts with the weak base part of the buffer. So you need to know how many moles of the weak base are present. So I would do a little bit of math with this one. I would say I got 250 milliliters here. I'm going to convert that to liters. So, and then I was given this information here. H2. All right. And then I would honestly just do dimensional analysis here. So this would be and I'm left with 0.014 mole. And the reason we're only dealing with this is because we're asking how many moles of the strong acid could be added to the buffer, so you don't need this information. So you just want to make sure you're comfortable with identifying which one's the acid and which one is the base. So looking at this, mathematically, the answer would be B. Would not create a buffer solution. Okay, so this is just asking you to identify which of these does not leave a weak acid base pair together in the right way to make a buffer. So remember that the buffer is a weak acid and its conjugate base together, or a weak base and its conjugate acid together. So looking at these options, I would just go through and check, that they make sense. Um, this doesn't make sense. This and this doesn't make sense. I'm going to throw this out. K, H, 2, PO4. This doesn't really make sense to me. This definitely doesn't make sense. CH3 and H2, CH3, H3Cl. Again, not really making sense here. So these don't look like they, wait, am I reading? Which of these would not create? Yeah, so these two would not create ones. The rest of these would create. Sorry, sometimes you got to make sure you're reading the keywords properly. All right, so this one's a little tricky because this one is saying not to create a buffer solution, meaning something that isn't its weak acid and its conjugate base or a weak base and its conjugate acid. So just be very careful that you're reading what it's asking, not which ones create a buffer solutions, but which ones wouldn't. So I would look through each of these and see do these pair together as a weak acid and conjugate base pair. So this makes sense because this is, they up one, this is just a spectator ion. So this would create a buffer, CH3 and H2, 12 moles of this, these would react. H3PO. Okay. This would, this would, this would, this would. This one doesn't even have. This one is questionable. NaH3. This one gave up its hydrogen. So this one would also make a buffer solution. So the one that's most questionable to me that I think would not create a buffer solution is D. Which of these following statements about spontaneity is true? All right, so this question is really asking like, what is the real meaning of spontaneity? A spontaneous process is one that increases the entropy of the universe. It does not have to be fast and it doesn't have to be exothermic every time. So that's something to look at here, like when it has things like it has to be something. So with spontaneity, right, of the universe is greater than zero. So that means this is spontaneous, right? And this is what's saying is true. Um, we also know that delta G is less than zero. All right, so spontaneous does not always mean fast, right? Spontaneous does not always mean exothermic. And spontaneous does not mean that the energy of the universe increases. Fast and spontaneous are not the same, so don't mix those up. A lot of people do sometimes. Um, the thermodynamics just tells you if something is favored, and the kinetics just tell you how something fast is. So reading these answer choices, I would say that the answer is A. All right, let's look at 8. For the combustion of methanol is shown below. Okay, so this is asking to calculate that delta S, not of the reaction. These are on a couple different problem sets that we did in class. So you use the formula, the um, delta S is equal to my sum is not very good, but sum of the products minus the sum of the reactants. So we're just going to look at our chart. First thing do, just in case, you always want to make sure everything's balanced so that way we're using proper stoichiometry. We're going to look at CO2 here. So we have 2 of our 213.8 and make sure that we're adding all of our products together. So I have plus 4 times my H2O, 188.8. Put those in brackets and we're going to subtract it from 2 of our 239.9 plus 3 of our O2's 205.2. All right, when you do that math, you should come up with something very close to 87.4. So answer is E. Okay, so at all temperatures, okay, so we're spontaneous at all temperatures. Reaction occurs with an increase in entropy. What must be true about this reaction? Okay, so something at all temperatures, that means that our delta G must always be negative. If we have an increase in our entropy, so that's going to be our delta S has to be greater than 0. We also need to make sure that our delta H is less than 0 if it's going to be spontaneous at all temperatures, which means it's exothermic. I don't know if I spelled that right, exothermic. All right, so this question is really asking what sign of the enthalpy must go with the reaction that is spontaneous at all temperatures when entropy is increasing. So since delta S is positive, and the only way delta G stays negative at all temperatures is if delta H is also negative. So that must mean that the reaction is exothermic. So looking at that, the reaction or the answer is C. And you should memorize, or not memorize, but understand and like the delta H chart and the delta S chart, and when it's spontaneous at the temperatures. I'll just quickly write that out. And it's very important that you're able to utilize this in a test. But so if I have our delta H is negative and delta S is positive, for spontaneous at all temps. Delta H is positive. Delta S is negative. We're non-spontaneous at all temps. Delta H is negative and delta S is negative. So we're spontaneous at low temps. So this is key, right? Low temps. If delta H is positive and delta S is positive, that we're spontaneous at high temps. So if you can remember this, you'll be in really good shape. All right, let's move on to 10. The following reaction is exothermic. Okay. What statement is true? All right, so if the reaction is exothermic, we know that delta H is less than 0. We have another thing we're going to look at is how many gas moles we have. We went from 1 to none. So, knowing that we had gas on the reactant side and no gas on the product side, what does entropy do? It decreases. So we have our delta S as less than 0. This combination, going back to our table above, means that it probably means that spontaneous at low temps, and it's not spontaneous at high temps, right? So knowing that, I'm thinking, so this one is not at all temps, non-spontaneous, no, it's spontaneous only at high temps, and we just determined it would be a low temp, so C's out. It's spontaneous only at low temps. Yeah, that sounds right. Not enough information. They gave us enough information. So the answer to this one would be D. Dry ice sublimes. So this is a key word to form gases. Right? The enthalpy of the system what and the entropy of the system what. Okay. All right. So remember what sublimation is? This was, I think, on a test prior, but that means that we're going from a solid to a gas. Um, so energy has to be absorbed to separate those particles, so the enthalpy would probably increase since it's absorbing that. And gas has so much more disorder than a solid, right? Solid is like the least. It always goes like solid, um, liquid, and then gas. And so, with it being sublimation, going from solid to a gas, I would say that the entropy goes up, again, because gas has a lot more disorder than a solid. So, looking at this, I would say that it increases and increases since energy has to be absorbed. So, that means that enthalpy is increasing, and gas has a lot more disorder. So, the entropy is also increasing. So that's an increase to an increase. Calculate the value of Kp for the reaction below 298 Kelvin, and whether it's reactant favored or product favored. Okay. So this one is, asking to connect the logic of Gibbs free energy, right? And the equilibrium constant. So this is on the exam information sheet. So you're given the enough information to use one of the formulas on the sheet. So looking at what information we were given, I would go, okay, I think I need to use the delta G naught is equal to negative RT log of K. I was given delta G, but I'm going to convert that into joules just so that the um, constants or the signs all work together. So I'm going to make that 9800 joules. R is a constant, that's 8.314, and I was given my temp, 298 Kelvin. What I don't know is what it's asking for is K is my log of K. So I rearranged my equation to get log of K by itself. I guess natural log. Is equal to put our delta G up there. So negative, make sure we keep our negative signs. Joules over our constants, these here. 8.314298. That should give me negative 44.3. So now I've got, I want to get rid of my natural log. So I have K is equal to e to the power of negative 44.3, which should roughly give me 6 times 10 negative 20. So I can immediately get rid of A and B and E. All right, so this K is like super, super small. So right there, that would tell me that the equilibrium is reactant favored. And something to remember when it comes to this, just as a trick, a positive delta G means a small K, and a negative delta G means a large K. So if it's a very small K, it's just reactant favored. So knowing that, I would say the answer is C. Okay, so for 13, again, I'm using changes in Gibbs free energy, and I'm gonna write out what I know in order to kind of keep everything straight. Um, we have our delta G, we have two, two. Okay, it's already balanced. We're just gonna throw it into our equation. One 1.53. This is 2 moles of K. So, the balanced equation shows that negative 761.4 kilojoules corresponds to 2. So that's where we get our stoichiometry from. 2 moles of potassium. And since only 1.53 moles reacted, that's why I multiplied that over 2 and got the negative 582 kilojoules. So the answer here is B. Reaction. So this question is asking for Gibbs free energy under like non-standard conditions. So I would probably use the delta G is equal to the delta G naught plus the RT natural log of Q. I think Dr. Outlaw wrote this on the board, I don't know if it's on the exam information sheet, but it's the other equation to remember. It might be on the exam information sheet. So knowing this, I would just write out what we know to start off with. So I'm going to use this equation. U is equal to the pressure of, because we don't care about liquids, pressure of NO2, but there's 3 of them, so I want to make sure I cube it. All right. I was given their atmospheric pressures. All right, so that out. Oh, I messed up. I put 0.01. I gotta fix that. Oh, 637.907. Okay. All right, so I was given the rest of the information. So I'm gonna write out, and your R, you can either you can go either direction, and if you want to keep the units in kilojoules or if you're going to keep them in joules. So just make sure you're either converting R or your delta G into like units. And then that was given 25, so that's 298.15. And then I've got natural log of my number here, 6,377. I'm going to keep my at least one extra digit. So you should be able to throw all that in. See, natural log 0.7. Okay, so I got 9.4 plus 2.478 times I got 8.7605. Continuing on, and that would equal delta T should be 31.1 kilojoules. Ah, answer is E. All right, so if you have any additional questions, please let me know.